Well, thank you. Good morning, everyone. It's the morning after the banquet, so I know it's rough to drag myself out of bed early in the morning comes to a talk. So I salute your hardcoreness, and I'm honored to be in the presence of your hardcoreness. Also, thanks to the organizers for the opportunity to talk and putting on such a great semester program. It's really been a great time here. So yeah, I'm going to talk about something, power operations, or spectra. So this is stuff that is joined with Tom Bachmann, who is here, and Elden Elmanto, who isn't. We have 3 papers posted on the archive recently, so everything I say will be contained in those, but there's a whole lot more there, so be sure just take a look. Right, so we should get started, and I guess we may as well start in the beginning. And so, what is there? So in the beginning, there is singular cohomology. And what we learn in school is that singular cohomology is it's really good, and part of what makes this a good thing is that, well, it's a commutative ring that turns us into a commutative ring, but in fact it's much, much better than that. You have action of these Steenrod operations, and these Steenrod operations are really the key to the success of this gadget here. Makes this such a good thing. And the source of these Steenrod operations, this is pretty interesting. As well, you don't need me to tell you how interesting this is. But so the source is the fact that this this commutative ring structure here, this cut product, this lifts to the cochain level, and on the cochain level, this isn't commutative; it's only commutative up to homotopy. The source of these operations is multiplication on the cochain level, which is only commutative up to homotopy. And so this idea of multiplications that are commutative up to homotopy, of course, there's a long, rich story here that it would be hard to underplay the importance of it. But so this leads to notion of E-infinity ring spectra, and well, there's lots of things to say here. I'm talking about power operations, so the homology of any E-infinity ring has these power operations, these Dyer-Lashoff operations. Let's see, they do this, Qi. And E here, this is the E-infinity ring. Okay. And maybe one of our favorite examples of an E-infinity ring is the Eilenberg-MacLane spectrum itself. So E. HF2, and then what we're looking at is the dual Steenrod algebra. So usually written as A. Actually, this is very simple. It's a polynomial and infinitely many generators, so it's a Hawk algebra. This is the underlying and again, this is an object of fundamental importance. Well, let's see. So here's a great theorem. So this dual Steenrod algebra. So this is polynomial and infinitely many generators. That's nice, but still have infinitely many generators. So what Steinberger tells us, this great classical theorem, is that if you admit the Dyer-Lashev operations into evidence, once you admit the Dyer-Lashev operations into evidence, in fact, you have a single generator. So let's see, I think we can put this like this. And so the key thing I want to emphasize here is we have a single generator under the action of these Dyer-Lashev operations, and so as you might imagine, this is pretty powerful. So there's a whole lot of things we can say here about the utility of this. Here's one neat thing. So if we have an E infinity ring, with pi naught F2, then in fact this is a major restriction on the form of E. So E is a graded Eilenberg-MacLane spectrum. So in other words, it's a sum of shifts of Eilenberg-MacLane spectra. And let's say here this is additively. That's what it shows. Right. So maybe it's worth saying you can in fact do better than that. Maybe it's not relevant to this talk, but maybe I'll mention that you can say more here. So let's see, this is independently due to Vogler and Hausdorff. They show that if you have so if you have a homotopy commutative ring, so this is less structure. So they show if you have a homotopy commutative ring R in which 2 is equal to 0, then in fact R is and as a homotopy commutative ring spectrum is graded Eilenberg-MacLane. So this is as homotopy commutative homotopy commutative ring spectra. This is of course completely false as E infinity ring spectra. On a graded Eilenberg-MacLane spectrum, you can have multiple E infinity ring structures. By no means unique. Okay, so right, and well, let's see. There's more that we could say classically, classical applications of Steinberger's theorem. But maybe that's enough for this, I'm interested in something slightly different. So in this day and age, there's a whole lot of Steenrod algebras wandering around out there in nature, ready to bite you on the leg. And the one that I'm most interested in is the motivic one. So motivic dual Steenrod algebra. Let's see, this is bi-graded. You get it as the motivic homotopy of, so you take the motivic cohomology spectrum, the McLean spectrum, tensor with itself, and so this is a Hopf algebroid. We could write down the underlying ring. I'm not going to do that. Let me just point out that there are infinitely many algebra generators. Got everything like this. And so there's a base wandering around here. Let me just fix once and for all. I will forget about it. So this is a quasi-compact, quasi-separated base scheme with two invertible. Right. Let me state a theorem. So I'll state a theorem and then try to say something about it. So the theorem is that, well, one, there's operations. That do the following. So they do this. They shift both degrees indicated, and so the dual Steenrod algebra. So the statement is a version of Steinberger's theorem here. So it's going to be that this is generated by a single element under the action of these operations. So this is generated as an algebra over the coefficients under the action of the QI by this single element. Okay. Yeah.
In the grading there, is it 2 star for sorry? Or because if I
Sorry, where?
in the dialogues of the classical ones. Trying to
There's different gradings. There's different ways to index them.
right. I'm trying to understand. So if you take C1 and U1 on C1 has degree 3.
Oh, you're asking. Sorry. You're asking what are the degrees here? If I'm not mistaken, that's the degree there. Is that what you're asking?
Q1, Q2. Yeah. No, that's fine. Everything good. That's fine.
In that theorem of Steinberger, These generators that you've written down with iterated queues, are they actually just the same as the usual generators or not?
I don't think those are the same as the usual generators, if I'm not mistaken. I mean, the degrees don't seem to match up to the usual generators. Or unless...
The degrees are right, they're just, I didn't decompose it. I had decomposed it.
It's too early for me to count.
Also depends on what you mean by usual.
It's too early for me to speak English. But is it too early for me to erase the board German style? Let's see. Right, so, okay, so the goal of today, I want to say something about the construction of these operations, and say something about what we need to compute to prove that theorem. So yeah, so let's see how far we get. So the very first thing that has to be done here is to sort of explain something about the correct multiplicative structures here in motivic homotopy. So this is analogous to stuff that Mike was talking about on Monday, where different multiplicative structures you can have in algebraic homotopy. So what are the analogs of commutative rings? And so Bachmann and Bachmann-Hoyois have developed a very elegant theory that answers this this question. So they developed this theory of normed motivic algebras, spectra. So these are the, if you like this kind of terminology, these are the so-called genuine motivic E-infinity rings. The word genuine is arguably overused and abused. I'll try to avoid it, but maybe let's back up a second before trying to say something about what are these, what are motivic spectra. So luckily on Tuesday, Tom already explained everything there is that we need to know about the homotopy theory. We start off with some complicated category, make it bigger, and then make it impossible to understand. The localization, the category of motivic spaces is, these are just the A1 invariant Nishnevich sheaves. And okay, so we're gonna stabilize, and so what we do to get motivic spectra is we invert. So we invert a sphere. Here our sphere is P1 pointed at infinity, and maybe I should, if I'm gonna write it like this, I should look at the base spaces here. And so these are, let me look at the spectra. So this is a nice symmetric monoidal stable infinity category smash product. I'll just write as a tensor. And so what are the ring spectra here? So let me stay on an informal level. It's much too early for the full technical definitions here. So an E infinity ring informally consists of, well, we have a spectrum X. Well, it's a ring, so we have some multiplications, and we specify the n-fold multiplications for all n. And this is supposed to be commutative and associative up to homotopy, in fact, up to all higher homotopies. And so that's just plus coherences. And of course, as you know, this definition makes sense in wide generality anytime you have a symmetric monoidal infinity category. That's what symmetric monoidal is for. So this could be, in particular, you know, a classical spectrum or a G spectrum or a motivic spectrum or whatever. So what Mike talked about on Monday, you probably didn't call them an infinity, but G commutative rings. So informally, this is a G spectrum together with data of now the multiplications are, so it makes sense to do tensor power by a finite G set, and now you ask for having multiplications parameterized by finite G sets, and then you have coherences. And so now the norms motivic spectrum is, so informally, this is it's a motivic spectrum together with a whole bunch of multiplications. So the analog, so this is maybe this pattern-wise, it's clear, analog of finite sets in G equivariant homotopy theory, that's finite G sets. Analog here in motivic, it's finite étale maps. Something slightly different happens in that finite étale maps, this changes as you change your base, so we have to account for that. So this is T maps to S, finite étale. And what we have is, so for a finite étale map, we base change X to S, and then now over S we have a parameterized smash power, and we ask for a multiplication like this, and that all has to fit together in a incredibly complicated way, but Tom and Mark worked out how to keep track of those coherences in a way that doesn't, you know, lead you to become totally insane thinking about it. So let's see, maybe quick remark, how to think about those smash powers. So you would hope that you get the usual smash power back out of this, and indeed you do, from exactly the ATOL extension that you expect. So if T is just the trivial extension, then this is just the usual n-fold smash power, and in particular, if X is a normed spectrum, it is E infinity. And maybe second comment is, what did these parametrized smash powers look like? So, well, in general, they're very complicated, but in one case where we can describe them, so let's say that we're looking at a actual smooth scheme. So W is a smooth scheme over the base, then this is, what is this? So this is given by the Bay restriction. So this is Bay restriction. And let's see, this was W, and I had to base change T in that. So it's just given by Bay restriction. Okay, so let's see. Anything else to say here before moving on? Any examples? Right. A lot of our favorite friends have this structure. So the sphere, motivic cohomology, K-theory, cohortism. Not everything is an example. This is not a triviality to have this structure. So maybe one of our favorite non-examples is the eta inverted sphere. So if eta doesn't mean anything to you, ignore this. But so, eta, so the Hopf map in the setting, it's not like, so this is a nice E infinity ring, but it's not normed. So it's not normed. In fact, Tom and Mark show something even cooler. So they show that whenever you have a normed spectrum on which eta acts invertibly, then that normed spectrum must be zero. So in other words, while eta isn't nilpotent in motivic homotopy theory, it is normed nilpotent, which and maybe a other remark.
If you use the real time, would that thing be normed in a sense which is more real if you invert it? If you use the real time instead of time?
I don't know.
No, please. Right, so why the name norms? So if E is norms, then the E cohomology, let's view as a functor like this on finite ATOL extensions of the base. So this is a Tambara functor. So analogous to Tambara functors that showed up in Mike's talk. You have, well, it's a cohomology theory, so you have this contravariance functoriality of rings, and then you have an additive covariant functoriality, the usual transfer. But now the new thing here is you have a multiplicative covariant functoriality, multiplicative norms, and that all assembles together into something that you can rarely call a Hamara functor. And the presence of that extra structure, the multiplicative norm, that's the source of the name for normed spectra. And so, for example, if B is a field, then the homology represented by the sphere on finite axial extensions of K is just given by the Grothendieck-Witz theory. So Grothendieck-Witz bringing non-degenerate symmetric bilinear forms over the base, and the norms here are called Ross norms. Marcus Rust.
What is the formula for restriction of the norm look like in this context?
The formula for restriction of the norm.
I mean, in the equivariant setting, you norm up and you come down and you get a product of concepts or something like that.
There's something similar. I don't think that I can say it off the top of my head. Right, okay, so so right, so let's drag this towards the construction of the power operations. So there's extended powers that play a key role in the construction of power operations. So just to remind you, the classical extended powers look like this. So you take the n-fold extended power, you take the n-fold smash power of x that now has an action of the symmetric group on n letters, you free it up, take the quotient. In other words, you take the homotopy orbits, or the co-limit of you take the homotopy orbits of that sigma n action. So that's what the classical one looks like. So the motivic extended power looks like this. So let's call that Bn modes. So this is now, instead of taking a co-limit over sigma n, we take it over so you're essentially taking a co-limit over sigma n forces, so finite axial extensions of degree n. And maybe one thing that I wanted to mention right here, so this appears in the free E infinity algebra generated on X. The free E infinity algebra generated on X is just given by you sum over all these extended powers, and we have something here, so the free normed algebra X is, I don't know if I need notation for this, but there it is, and sim, so that's given as some of these extended powers. Let's see, I think this version of this here's been already in common marks paper. And I guess Tom then proved a more general version of this later. So in particular, so why am I saying this? In particular, if X is norms, then you get multiplication. Back down to X. Now for the construction of these power operations here, we really only need n equals 2. That's not to belabor the point. Okay, so, yeah, so, how are we doing on time? Not excellent. So, here, maybe let's, let me jump ahead. So let me say this as follows. So for this for the construction, we sort of need two descriptions here of this extended powers functor. So here's a nice categorical co-limit description, but there's also a way to describe this via an equivariant homotopy type model, which will give us a geometric control on that down the road. So let me just say there exists an equivariant model, and without explaining what these things are, let me just write. So in symbols looks very similar to the classical description. So this thing here, this is a sort of enhanced smash power. It itself is really a special case of a norm type construction, but it lives in the sigma n equivariant motivic homotopy category over B, and this is a universal sigma n free motivic space, and this has a geometric description. So for example, for n equals 2, this is a co-limit of affine spaces with the origin removed, where the action is given by minus 1. So in other words, that's the sign rep. And in particular, when we look to the quotient here, what we get is, I think Morel-Blavatsky write this as BGM, so this is the geometric classifying space construction of Morel-Blavatsky. This is, as motivic spaces, this is equivalent to the stack of A-tall sigma 2 torsors. So this equivariant model, which is equivalent to the motivic model, and having this other model has several functions. So we have a diagonal. So that X is the suspension spectrum of a based motivic space. Then we have a diagonal here, and this lets you make the following definition. So let's say R is normed. Spectrum of quadratic R operations. Let's see. Indexing rates. This would be and run that R, and I should be careful about the order. Like this. So the structure maps here. So these use the diagonal. And the homotopy. So the homotopy groups of this spectrum, so they give rise to operations. Oh, let's see. Maybe let me match my indexing here. So let's say we have an element in degree mn there, then we get an operation that goes like this. And here this is a normed R algebra, and for the sake of time, I'll omit the explicit formula. You can write down an explicit formula for how you go from this to this, but so the second function of the equivariant model is you have, in the case where R is HF2, at least you have great control over the homotopy of this. So let's say the base now is this. Then so then this spectrum, the homotopy groups are free. On generators EI, so these have degree. Like this. And so the idea here is that, well, this extended power, so this is, can be written as a Thom space. So this is a vector bundle over B sigma 2. Let's see, that's n, so this is the sum of 2 rank n vector bundles. This one is trivial. And this is the sign rep. And of course, in HF2, you have the Thom isomorphism, so you can, well, you can then pack everything in the letter like that. And let's see. So in fact, so this maybe it's just say more things. So, right, so in fact, this is interesting. So this, the spectrum ops, if you take its suspension, you can recognize that as a Tate construction. And so in particular, right, so in particular, so here we understand this thing quite well. You can get, so you can determine the co-module structure there and transfer it over to here. This lets you determine the co-module structure on ops and well.
How was that exactly a Tate construction? Could you spell that out?
I didn't spell it out. I can maybe in 1 second you can. If there's further questions, you can ask me to say something about that. Right. So yeah, I'm out of time, and there's a whole lot of formula. So let me say the following. So to prove the theorem, so let's see. So to prove the theorem, what you do is well, you consider, maybe this is what I started to reference right there, so you consider this module structure. So you have power operations there, power operations there. This doesn't commute with them, but you can write down how this intertwines them. So those are the Kundashita relations. And together with the fact that you understand everything explicitly over there, you can get you can extract out of all of this formula, and what you get is for example, these formulas. So this is for K positive. And so, and this is all, that's all happening in the dual Skinner algebra. And so what you find is under the action of these operations, the conjugates of all of the generators are in there. And since the conjugates generate, in fact, these generate everything. And yeah, apologies for going over all over that.